Thank you very much, Carla, and thank you, Purdicom, for hosting this event today. Hello, everyone. My name is Daniel Ephraty, so I work for Siklu Communications. I look after professional services. I'm delighted to do this webinar today, and with me is Byron from Purdicom as well, a panelist on this webinar. So this is the first of a series of three. I mean, there's no particular connection among these three lectures that we're going to do. So this is number one. The second one is going to run next week, and the third one is going to run the week after. So if the topics are of interest, please feel free to join. I just want to say today's topic is quite general. It's got nothing to do with Siklu. Oh, I wouldn't say nothing, but it's got little to do with Siklu. It's not Siklu specific. Whereas the other two coming up next week and the week after are a lot more Siklu-centric. So please, if you haven't already, please join us for the next two sessions. So today, I want to talk about some general topics relating to wireless communication, right? And like I said, this is not just specific to Siklu. Anybody who works with wireless communication might be interested. And this came about through feedback we had over the years from people saying, you know, we don't really understand the basics. Can you elaborate on them? So today I've got three topics here that I want to go through. The first one is talk about decibels. I call it decibels and friends because there's some things that are related to decibels, which transmit power, antenna gain, and so on. That's section one. Section two, we'll just generally talk about modulation and coding. And section three, we'll talk about wireless propagation. Now, this is a relatively new slide deck, and I've only had the occasion to run it once before, and it did run over the hour. So I believe Purdicom has sent a note to say that this might run over an hour, but you know, if any of you have to leave on time, I completely understand, and a recording is going to be made available where you can watch anything that you might have missed. Okay, so first thing I want to talk about is decibels and friends. Now, this is going to be the most technical section of all. There's a little bit of maths involved, not terribly difficult, I hope. If you find yourself lost throughout, just hang in there. You know, my goal here is just to give you a general understanding of what decibels are, and not necessarily that you should be able to do any maths using decibels. Hopefully you will, but if you don't worry about it. It's still good enough if you get a general idea. So I want to start with some motivation to decibels, and here's a warm-up question for you, right? So if we wanted to know what is 40,000 divided by 0.00008. I bet most of you would just reach for the calculator because this is quite a difficult question to do in one's head. And the question is, why is it difficult? Okay, and I think there are two reasons why this particular math problem is hard. One is because we're working with very large and very small numbers. And also we need to divide, and division is quite difficult. You know, generally multiplication and division are more complicated than addition and subtraction. And this is exactly what dBs do for us. Now, you might think, well, why are you asking us such a question? Why should we care about what's 40,000 divided by this fraction? Well, this is because we do this all the time in wireless communication. So here's a practical example, right? One of our radios, one of Siklu's radios called the Etherhall 1200TX, has a transmit power of 3 milliwatts, and this is actually all true. And then if you put a 1-foot antenna onto this radio, it would amplify the signal 20,000 times. And then as the signal propagates over 1 kilometer, only 1 part in 10 trillion will reach the receiver. I mean, this is mind-staggering, but it's actually true. And then let's just suppose that we have a 2-foot antenna at the receiver end, and that would multiply this 100,000 times. So these are just all, you know, data. And then the question is, what is the receive power at the receiver? Say we wanted to calculate this. So we would actually have to go through this math problem, right? We would have to take the 3 milliwatts of transmit power multiplied by 20,000, which is the gain of the transmit antenna, then divided by 10 trillion, which is sort of the loss that we have when the signal propagates, and then multiplied again by 100,000 because that's the gain of the receiving antenna. So this is the kind of questions, these are the type of questions that we have to work with all the time when we do wireless communications. And obviously, it's a very difficult exercise to do in one's head. So hopefully, I will convince you over the next half hour that if you do these kind of questions in decibels, as opposed to normal numbers, the problem becomes much simpler and is even possible to do it in one's head. Okay, so how do decibels work, right? So we said that we had two difficulties. One is that it's hard to work with very large and small numbers. And what we do in decibels is we convert these very large numbers and very small numbers to small numbers, numbers that we're happy to work with. And the other difficulty we said is that it's hard to multiply and divide. And so instead, what we do in decibels is we add and subtract. So addition and subtraction are obviously a lot easier to do than multiplication and division. So let's go back to our warm-up question. And I just want to show you how it works. I know you won't understand every single step of the way, but just as an outline. So our warm-up question was to divide 40,000 by this fraction 0.00008. And so how would we go about doing this in decibels? The first step is we would convert these large and small numbers into sort of normal numbers. So the 40,000 would convert to 46, and this fraction would convert to -41. And then we would substitute the subtraction for division. So instead of dividing, we'd subtract, and then we'd have to do 46 minus -41, and that's quite easy to do. Okay, that's just like 46 plus 41, so obviously it's 87. Okay, easy to do. And then we convert this back in from decibels into a normal number, with the result being 500 million. So that is the answer of that math question. And the only thing that remains to do is to explain to you how we converted 40,000 into 46 and how we converted 87 back into 500 million. But once you know that, you see these questions become a lot simpler. So hopefully that gives you a good idea of why decibels are important, how we do complex math questions relatively simply when working in decibels, and hopefully you're interested to know a bit more about this. So yeah, easy, right? So let's just start talking about how we actually convert numbers to decibels, right? So for this, you're going to have to memorize a few things, but not more than 2 or 3 different things. So it's not terribly difficult. So the first thing to memorize is that the number 1 translates to 0 dB. So saying 0 dB or saying the number 1 is just the same. The second thing you have to memorize is that every time you multiply a number by 10 or add a 0, as it were, so you go from 1 to 10 to 100 to 1,000 to 10,000 and so on, you just add 10 in dB. Right, so for example, if I wanted to convert the number 10 million into dBs, I would count the zeros. So there are 7 zeros there. That means that I started with 1 and I multiplied it by 10 7 times. So that's very easy. I start with 0 because we said 0 dB corresponds to 1. And then we add 10 every time the original number multiplied by 10. So 10 plus 10 plus 10 plus 10, we have to do that 7 times. And we get 70 dB. So indeed, 10 million translates to 70 dB. Easy. You count the zeros on that large number, and that is multiply that by 10, and that's your number in dB. So here are some other examples for you, just so you get a good idea of how it works. So for example, if I wanted to know, let me just get a highlight pen. Here we go. There we go. So no, that's not quite it. Spotlight. There we go. So if I wanted to know what the number 10 translated to, I would say, okay, well, 10 is 1 times 10. So 1 we memorize translates into 0. And times 10, we just learned we have to add a 10. So that gives us a total of 10. And if we wanted to know what 100 was in decibels, we would say, well, 100 is just 1 times 10 times 10. And so the 1 translates into 0, and the times 10, every time we multiply by 10, we add 10. So we get 0 plus 10 plus 10, that's 20. In other words, count the zeros. And when we have 1,000, that's got 3 zeros. So in dBs, that's 30. 3 zeros times 10. Okay, so hopefully you're still with me. Right, now that was about large numbers. When we have small numbers, what we have to do is subtract 10 every time the number is divided by 10, because we're replacing division by subtraction. Okay, alternatively, it's easier to count the number of decimal point shifts. So, for example, if I wanted to know what 0.1 is in decibels, well, I would say, well, okay, 0.1 is just 1 divided by 10. So 1, we know, translates to 0. And divided by translates to minus. Divided by 10, that's minus 10. So we get minus 10. So basically, 0.1 is neg 10 dB. Okay, and equally 0.01, that we had to divide 1 by 10 twice to get to 0.01. So in dBs, we would take 0, subtract 10 twice, and get to neg 20. Now, it's easier if you get a very small number like this, is just count the number of shifts that you have to shift the decimal point to get the number 1. So here, I would have to shift 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 shifts. And therefore, that in dB would be neg 90 dB, because I started with 1 and I divided it by 10 9 times. So every time I divide by 10 in dBs, I subtract 10. So division goes to subtraction. Okay, guys, I hope you're still with me, but you see how very large numbers, like the one we have here, 100 million, goes to a relatively normal number like 80, and this really, really small fraction we had here goes into another relatively convenient number like neg 90, okay, in dB. So that is the basics of it, and I just want to add one more thing for you, is that in dBs, when you multiply by 2, you add 3 dB. So that's another thing you have to memorize. And here's an example, right? Say I wanted to know what 20 was in dB. So I would say, okay, well, 20 is just 2 times 10. 2, we know, goes to 3 dB because we've just learned this on this slide. And the times 10, we have to add 10. So 3 plus 10 is 13. So really the number 20 translates to 13 in dB. And if we wanted to know what 400 was in dB, we would say, well, 400 is just 2 times 2, which is 4 times 100, because it's 4 times 100. And the 2 times translates to 3 dB. So we've got 2 here and 2 here. That translates to 3 and 3. And the 100, we remember we just count the zeros. There are 2 zeros there, so that goes to 20 dB. So we would have 3 plus 3 plus 20. That gives us 26 dB. Okay, and here's our 80,000 from a warm-up question. So we'd say, well, 80,000 is just 2 times 2 times 2, because that's 8 times 10,000. And so every time we multiply by 2, we add 3. So we've got 3 plus 3 plus 3 is 9. And the 10,000, that's got 4 zeros on the end. So that would be plus 40. So that is 49. Okay, and of course, when we divide by 2, then we subtract 3 dB. Okay, because division goes to subtraction. So for example, if I wanted to know what 5,000 was in dB, then I would think, well, 5,000 is just 10,000 divided by 2. So the 10,000, it's got 4 zeros, that translates to 40, and divided by 2 translates to minus 3. So 40 minus 3 is 37. Okay, so hopefully you see that it's not too complicated and relatively easy to do. There's one more that you might like to memorize. It's not that important. It's only if you want to impress people, is that multiplying by 3 is like adding 5 dB. Actually, accurately, it's adding 4.8 dB, but most people just think of it as 5 dB. But that is not strictly necessary. It's just if you want to really impress your friends, your geeky friends, then memorize this as well, that multiplying by 3 in dB means adding 5, and of course, dividing by 3 in dB means subtracting 5. Okay, so some examples here. If you did want to show off in that way, so 300 would be 3 times 100. The 3 translates to 5 dB, the 100 translates to 20, and then you add them up and you get 25 in dB. So just a few examples on there for you. I won't go through them now. Hopefully you get the idea. Okay, now what I've done up till now is just explain it to you as intuitively as I can, because this is how I actually think of dBs. But they do have a formal definition. So in order to convert a number to dBs, you have to do this complicated formula here. So if we wanted to convert the number x to dB, we would have to take the logarithm base 10 of x and multiply the result by 10. So, you know, when you look at that, you kind of think, oh gosh, I need to reach for my calculator. And this is why I went through all these other tips, which would just prevent this. But if you wanted to do this formally, this is what you would do. So here's an example. Say we wanted to convert the number 25,000 to dBs. So we would take 25,000 and take the 10th logarithm of that. So if you do that on your calculator, you would get 4.4, and then you would multiply that by 10, and you would get 44 dB. Right, but guys, we already knew that because 25,000 is like 100,000 divided by 2, which is 50,000, and again divided by 2. So that gets us to 25,000, and we already know how to do this, this exercise. So 100,000 has 5 zeros on the end, so that translates to 50. And every time we divide by 2, we subtract 3. So 50 minus 3 becomes 44. Okay, so you see how you can reach the same result easily and simply without actually having to grab your calculator and use this formal definition. Now, what about the reverse? If we had a number in dB, say y dB, how would we convert it back to a normal number? Okay, so here's the formula for you. You would take that y dB, you would divide it by 10, and then you would do 10 to the power of whatever result you just got. So here's an example. Say we wanted to convert neg 13 dB into a normal number. So what we would do is we would divide neg 13 by 10. That would give us neg 1.3. And then we would use our calculator to compute what is 10 to the power of neg 1.3. And the calculator would say 0.05, right? But again, guys, we already know this because neg 13 dB is the same as neg 10 dB minus 3 dB, because neg 10 minus 3 is just neg 13. And to convert neg 10 dB, we know that's just 0.1, because that was one decimal shift. And to convert the minus 3 dB into a number, that's one of the things that we memorized, just means divided by 2. So 0.1 divided by 2 is 0.05. Okay, so same result, but without resorting to a calculator. So, but you've got these formal definitions here. Okay, so far for dBs. Now I want to talk about one of the friends, and this is dBm. Okay, so dBm is related to dBs, but it's something different. Remember, dBs, just decibels, are just a clever way of doing maths with very large number and small numbers. dBm is totally different. It's about measuring power. Okay, so normally we measure power in watts or milliwatts. In wireless communication, we use milliwatts because a watt is a very large amount of power. So a milliwatt is just 1 part of 1,000 of a watt. So 0.001 of a watt. That's a milliwatt. And so we define 0 dBm as 1 milliwatt. So instead of saying 1 milliwatt, we say 0 dBm. It's exactly the same. And from here, we use normal dB math. So let's take an example. I mentioned that before already. So the Siklu Etherhall 1200TX has a transmit power of 3 milliwatts. And say we wanted to know, well, what is that in dBm? So we would just say, well, 3 milliwatts is 3 times 1 milliwatt. Okay, and we already know that 3 times, that is one of the things that I told you that were extra to memorize. So 3 times would mean 5 plus, because 3 translates to 5 dBm and the times translates to plus. And I just defined 1 milliwatt as 0 dBm. So 5 plus 0 is 5. So 3 milliwatts is the same as 5 dBm. This is how you convert from power to dBm. Okay, so remember, 0 dBm by definition is 1 milliwatt, And from then on, it's just normal dB math. Okay, let's take another question with a small number. So here's another of our radios. This is the Etherhall 1200FX, and it's got a sensitivity of -86 dBm. So the sensitivity is the minimum amount of power the receiver needs in order to make out the transmission, in order for the link to lock, in order for you to be able to retrieve your data across the link. This is the sensitivity. So -86 dBm, say we wanted to know what that was in milliwatts. Okay, so, well, -86 dBm, that's like 0 dBm. Remember, we always want to talk about 0 dBm because we define 0 dBm up here as 1 milliwatt. So we would start with 0, and we'd say, okay, well, how do I get from 0 to -86? Well, easy then. We'd subtract 80, that gets us down to -80. We'd subtract 3, that would get us down to -83, and again, we'd subtract 3, that would get us down to -86. So once we've broken it down to 0, -80, -3, -3, then we start converting into normal numbers. So the -80, that would be 0.1, 0.000. Remember, we have to shift the decimal point 8 times. So that would tell us how many zeros to put in here. And every time we need to subtract 3, we divide by 2. That was one of the things that we memorized. And so 0.0000001 divided by 2, divided by 2, that brings us to 0. Well, it's a long number. I won't read it out, but you can see what it is here with 25 at the end, milliwatts. But you can see this is a really tiny, tiny fraction of a milliwatts. And I think that's quite impressive. And imagine that's all the power that's required for the 1200FX to lock onto a signal. You know, it's just the faintest of whispers. And if you think about that, that number is 1 part in 400 million. So imagine 1 part in 400 million of a milliwatt is enough for the link to lock. I think that's absolutely astonishing. Okay, so now you know what dBms are, and there is a related term, which is dB watts. Okay, so we write this out as dB and then W, dB watts, and that 0 dB watts is defined as 1 watt. Okay, and like I said, we don't really use that in wireless communication because that is a very large amount of power. But you might see it on some forms. For example, if you're filling in an Ofcom license form, they do ask for things in watts or in dB watts. So it's important that you know how that relates. So because we know that 1,000 milliwatts go in 1 watt, okay, that means that 30 dBm is 0 dB watts, okay? Because 0 dB watts is 1 watt, and to get there from milliwatts, that would take us 1,000, and 1,000 in dB is 30. So 30 dBm. So 0 dB watts is 30 dBm. And conversely, if you're looking at 0 dBm, which is just 1 milliwatt, then that would be -30 dB watts because that's 1 part in 1,000 of a dB watt. Okay, dBm. Next, I want to talk about another friend, which is dBi. Now, dBi helps us measure the antenna gain. Okay, so antennas have a gain, and that's their ability to focus the transmission in a particular direction. And we define 0 dBi as the gain of an isotropic antenna, hence the I, okay? dBi means 0 dB isotropic. And basically, an isotropic antenna, you may not know, is an antenna that transmits uniformly in all directions. You can think of it as a sphere. So basically, if you had an isotropic antenna, which is just a hypothetical thing, because we can't really implement such an antenna, but if we did have one, it would radiate equally in all directions. So such an antenna we define as 0 dBi. Now, you may have heard of an omni antenna, okay? It's almost like an isotropic antenna, but in reality, it transmits uniformly in all directions except up and down, okay? So it's not quite an isotropic, but you know, it's easier for you to think of an isotropic antenna as an omni antenna. Go ahead and do so. That's fine, that's close enough. Okay, so here's an isotropic antenna. You see it kind of radiates, it's like a bagel. It radiates in all directions except for up and down. Right, now what is an antenna gain? So we define an antenna gain. We're asking, well, if we have a specific antenna, by how much does it focus the transmission in a particular direction, which is a direction of interest, relative to an isotropic antenna, right? So imagine you have a point-to-point link and you want one antenna to point and focus all the energy in the direction of the other antenna, right? So if you think of, well, how much does it focus it in that direction compared to an isotropic antenna, that would be the antenna gain. Okay, and so just as an example, we have a 1-foot antenna that operates in E-band, which is 1780 gigahertz, and that has a gain of 20,000. That means that if you point it correctly at the far end would receive 20,000 more power, 20,000 times the power it would receive if you had used an isotropic antenna. Okay, and we know how to convert that now to dBIs. So that is 43 dBIs. Why? Because 20,000, remember, is 2 times 10,000. So that's 3 plus 40. So here we have 43. And because we're comparing to an isotropic antenna, we say 43 dBi. Okay, and our 2-foot E-band antenna has the gain of 100,000. So 100,000, you count the number of zeros. We have 5 zeros here, hence in dBs it's 50. And because we're talking about a gain relative to an isotropic antenna, that means 50 dBi. Okay, so hence we specify that antenna as having a gain of 50 dBi. Okay, and just for those of you who are used to omni antennas, like the ones on walkie-talkies, they, like I said, they're very close to isotropic antennas, and they have a gain of approximately 2 dBi, a little bit less, sometimes a little bit more, but approximately 2 dBi. So they're not really that much better than an isotropic antenna. We know, you know that 2 dBi is less than 3 dBi, and 3 dBi is 2 times. So these omni antennas focus the energy in less than twice as much as an isotropic antenna would. Okay, so let's put it all together now. And after we've learned all of this, and I'm going back to the example I gave you before. So remember our Etherhall 1200 TX link over 1 kilometer, and we wanted to compute what is the receiver power, right? Knowing that the transmit power is 3 milliwatts, that we're using a 1-foot antenna which amplifies as 20,000 times, that propagates over 1 kilometer, and only 1 part in 10 trillion reaches the receiver. And then we've also got a 2-foot antenna at the receiver which amplifies this 100 times. And we said, well, we know how to work this out. We have to do this math problem here, but it is difficult to do. So let's just see how we would go about doing this in decibels. Well, we would just then convert every number to decibels. So remember, 3 is that fancy one, which I said translates to 5 dB. 20,000, that's 2 times 10,000, so 3 plus 40, 43. Here, this very large number, 10 trillion, we would have to count the number of zeros, and I counted there 13 zeros there. So that translates to 130. And then there is another 100,000 here, there are 5 zeros, translates to 50. Convert each multiplication to a plus, each division sign to a minus, and this is what we have to do now. 5 plus 43, so that's 48. Then we have to take away 130, and then we have to add 50, and we get neg 32 dBm. If we wanted that in watts, we would then have to convert it back. Now, I haven't really taught you what to do with neg 32, so let's just suppose that it's really neg 33, okay? It's not much of a difference, but we know what to do with neg 33. That's neg 30 minus 3, so neg 30 translates to 0.01, because that is a shift of 3 places, and the minus 3, we know, translates to divided by 2, so that is the number here, 0.0005 milliwatts. Okay, so I'm hoping I managed to convince you that dBs are useful and they're not so hard to work with. There's a few things you need to know, a few principles, how to convert numbers, and then convert the operations of multiplication and division into addition and subtraction correspondingly. And then hopefully this really simplifies your dB maths. Right, I want to see if there are any questions. I don't see any, so I think that's good. Do we have any on the chat? No. Okay. So guys, hopefully that was all clear. If you've all gone comatose, please wake up now, because we are moving on to the second topic, which is modulation. This topic is a lot less technical. It is technical, but not half as much as what we did before. So let's get on to that. So before we talk about modulation, I just need to explain to you what a carrier wave is, okay? So a carrier wave is basically a perfectly oscillating wave, typically in a high frequency, right? In the case of Siklu, we operate in really high frequencies. So in our case, our carrier waves oscillate 70 billion times per second, okay? Another way to say that is 70 gigahertz, because a hertz measures the oscillations per second, okay? So that is a carrier wave. So here it is. It's a perfectly oscillating wave. Now, these waves have a very special attribute, which is really the basis of all modern communication, is that they're able to propagate over the air, okay? They are able to do that. And so what is modulation? Modulation is the method of slightly modifying these perfectly oscillating waves so they convey the information that we want to send to the other side, okay? And so how do we slightly modify this perfectly oscillating wave? What are our options? So one thing we can do is modify the amplitude of this wave, right? So we can change it. Now I've drawn it here. It's got a constant amplitude. You see, it's constant. So one thing we could do is change the amplitude. Another thing that we could do is slightly change the frequency, okay? The number of oscillations per second here is fixed, but we could slightly play with that a little bit. We could also play with something called the phase, which I will talk more about. And then if you play with both phase and amplitude, we get something called QAM, which I'm sure all of you have heard about, okay? QAM, and we'll talk about QAM in a little while. Okay, so this is modulation, basically. We take a perfectly oscillating carrier wave and we modify it in a minute way to carry the information. So as an example, I want to take AM, and I know all of you are familiar with AM because that's there in most car radios, or at least they were. And you know, this is quite a historical thing because amplitude modulation is very easy to implement way before we had digital communication, when everything was analog, when we still had valves instead of transistors. It was very easy to do. Hence, this is the sort of the first and foremost modulation method that kind of captured wireless transmission. So how does AM or amplitude modulation work? We start with our perfectly formed carrier wave that you see here in green, and then we take our information signal. So this information signal is not digital, right? This is something like speech or music. You see it varies very smoothly, right? So we take that, let's suppose that that is some kind of music, and then we use that and superimpose that onto the carrier wave, right? And so the carrier wave's amplitude changes completely in sync with this information signal, right? And that arrives at the receiver. All the receiver has to do is recover the amplitude. And that's quite easy to do. All you need really is a capacitor and a diode, for those of you who've done some electronics, and you've recovered the amplitude. Easy, simple, and inexpensive. This is why amplitude modulation was so successful. Okay. We have a question about sharing the slides. So yes, of course, we're happy to do that. Okay. Okay. Right. The next type of modulation that I want to talk about is phase modulation. And here I'm going to give an example of digital modulation. So what do I mean by digital? Digital means that the information we're sending across the link is composed of numbers, basically, okay, as opposed to, or digits, right? Hence the word digital, as opposed to something that kind of varies smoothly, like music or voice, as we saw before in the old times. So nowadays, I would say almost any transmission is digital, including radio, as you know, DAB, digital, not sure what the A stands for, but something broadcasting. Okay, so the information we have now are bits, okay, or their numbers. And what we do by phase modulation is we vary the phase of our perfectly oscillating carrier wave. Okay, so the first thing I just want to explain is what a phase is. So we define here as a perfectly oscillating carrier wave. And then if we look at one oscillation, so just one of the many, we define that as having 360 degrees. So that shouldn't come as a surprise to you because you probably learned about circles at school, and you know that we refer to sort of a full circle as 360 degrees. And it's exactly the same here with the carrier wave, right? So a full cycle. So let me, sorry, get my highlight again. Right, so a full cycle starting here, going up, going down, and coming back to a starting point. That is 360 degrees. And so we can take that and shift that by however many degrees that we want to. So here, where we have the peak, that's 90 degrees. Then we go back to zero, that's 180 degrees. Then we go down, 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 with the minimum is at 270 degrees. And then we go back to our starting point at 360 degrees. Okay, so here, for example, is a phase shift of 90 degrees. So this is 90 degrees. You see that at 90 degrees, the oscillation is at its maximum, right, at its peak. So when we say that we shift this by 90 degrees, it means that we start it at the peak value. And then we just continue as normal. So we go down and we come back up, and we've come back to where we started. Right, but we come back to our maximum because our shift was 90 degrees. So this is a 90-degree shift, okay? So we actually started from here and finish it just after, which would be there, right? So it's just a shift. It's just, imagine a sliding window which just slides along however many degrees we want it to slide. Here is an example of a phase shift of 180 degrees. So if we look at our original oscillation, which is here, so we've gone up, gone back to zero. This is 180. And from 180, we go down and then go back up. So if I shift the phase by 180, what would happen is that I would first go down, then back up, and then complete my cycle. So it's exactly the same, but I've just shifted my field of view by 180 degrees. Okay, so hopefully you understand these phase shifts now. And what we do is we use our information that is we want to send to the far end in order to shift the phase of our carrier wave. So let's see how that's done. I'm going to start with just two phases. So let's suppose that we've got two information bits. We've got 0 and we've got 1. And we map them to phase shifts. So let's suppose that a bit of 0 corresponds to a 0-degree shift. So that's just our original carrier wave. And an information bit of 1 corresponds to a 180-degree shift. Okay, so whenever we want to transmit the bit 0 to the far end, we would just send the carrier wave as is. Whenever we wanted to transmit a 1, we would shift it by 180 degrees. Now, this is sometimes called BPSK. Some of you may have heard about this. BPSK is binary phase shift keying. Why binary? Because we only have two phase shifts here, 0 degrees and 180 degrees. Now, sometimes we like to draw this on a little diagram, and I'm sure many of you have seen similar diagrams before. So what the diagram really means is, remember we are saying that 0, the bit 0 corresponds to 0 degrees. Just going to go get my pen again, my highlight again. So here it is. So we draw this graph and we say, well, it's customary to draw 0 degrees as the right side of the horizontal axis. And this green dot here, that corresponds to the bit 0. That tells us that bit 0 gets translated to 0 degrees. And then if we wanted to transmit bit 1, that means that we had to shift the phase by 180 degrees. So we shift by 90, that gets us to the vertical axis, and we shift by another 90, that gets us to the negative part of the horizontal axis. So that's 180 degrees. So you may remember this from geometry. It's exactly the same. So this kind of diagram simply illustrates what I put here in words, that the bit 0 corresponds to a 0-degree shift, and the bit 1 corresponds to a 180-degree shift. Okay, let's see how that works in practice. So let's suppose now that we need to send across this information. So we've got a stream of bits, which is actually what happens in reality, because this stream of bits would represent a file or some telephone conversation or DAB, as we said before, or whatever it is, you know, emails or browsing the web or whatever it is. Ultimately, it all translates to bits. So here we have a bit sequence to transmit. So we're going to go from left to right. So 0, 1, 0, 0, 1, 0. And what we would do is we would then take our carrier wave and we would insert these, the corresponding phase shifts. So we are starting with 0. This is our first bit here. So here is 0. And that just means that we oscillate normally. Okay, there's nothing going on. Then when it's time to transmit bit number 1, remember, bit number 1 means, well, introduce a 180-degree shift. So remember that at 180 degrees, we oscillate. Instead of going up first, we go down first. So what we do here is we go down instead of going up, right? And this discontinuity here, this tells us that now we are broadcasting 1 instead of 0. And then we continue our normal oscillations until it's time to transmit 0 again. Now, 0, remember, we have to go to a 0-degree phase shift, which means we have to start and then go from 0 and then go up and then go down. So this is exactly what happens here. We go up and down and up and down and up and down, and we have another 0. So perfect, okay, nothing to do. We just keep going up and down and up and down. But where we have 1 again, we have to change the phase. We have to do a 180-degree shift. So instead of continuing to go up, we go down. Okay, and where you see these circles, this is exactly what the receiver looks at to work out whether there was a 0-degree shift or a 180-degree shift, and hence whether 0 was transmitted or 1 was transmitted. So this is phase modulation, two-phase modulation, or BPSK. Now, you see here that every time I'm transmitting just a single bit of information, 0, 1, 0, 0, okay? And that's quite slow. So if I wanted to speed this up, I could try and transmit more than 1 bit every time I had the opportunity, right? And this is called the higher order modulation, or high order modulation. What we want to do is increase the speed of transmission. And how do we do that? So we look at our information bits and we group them into groups. So these groups, technically, they're known as symbols, okay? But let's just think of them as groups. And then we modulate each group in one go. So for example, if we wanted to do 4-level modulation, right? And the title here is wrong. So that is a typo. I need to correct that. Let me just see, I need to get rid of this so I can correct this. This is 4-phase modulation, or QPSK, right? Okay, so what we do is we look at 4 levels and we group our bits into pairs, right? So if we had a pair of 0, 0, we might say, well, okay, 0, 0 then corresponds to a 0-degree phase shift. But if we had 1, 1, that was a group of a sequence of 2 bits of 1, we would then map that into a 180-degree phase shift. But if we had 0, 1, we would map that into 270-degree phase shift, right? So here is 270 degrees, so we draw the green line here. And if we had a 0, 1, we would map that into a 90-degree phase shift, okay? So these 4 green dots represent the 4 different combinations of 2 bits, because when you group 2 bits together, you can have 4 possible combinations: 0, 0, 0, 1, 1, 1, and 1, 0. Okay, so this little diagram tells us how we map bits into phase, and I've written it out for you here explicitly, just so you know, if it's easier for you to read this table, then read the diagram, and then we can go about doing this. Now, this is sometimes known as QPSK. Q stands for quadrature, and this is that word is because of the way we actually implement this, or we used to implement this in the past, right? But you might just think of Q as maybe quad and maybe 4, and hence we have 4 phases in QPSK. Okay, so here's an example. This is a stream of bits that we want to modulate using QPSK. So 0, 1, 0, 0, 1, 0, and so on. And the first thing we have to do is we have to divide it into pairs, because we're looking in groups, we're looking at groups of 2 bits each. So we divide that into pairs, and then we look at this table or this diagram, and we convert each pair into the corresponding phase shift. So this is how it's done. So the first pair we have here is 0, 1. So I put here 0, 1. Afterwards here I have 0, 0. So I put 0, 0. Then I've got 1, 0. So I put 1, 0, and so on. And then I have to look at 0, 1 and say, well, 0, 1 translates into a 90-degree phase shift. So the 90 degree, if you remember, that starts at the top, at the peak. So I start here at the peak, and then I oscillate normally. And then when it's time to transmit the next pair, which is 0, 0, so 0, 0 corresponds to 0-degree phase shift. So here I have to remember start from 0 and then go up and down. So I've got a phase discontinuity here, which I've highlighted in circle. And that discontinuity is very important, because that tells our receiver that there was a phase shift. Okay, and the receiver can then work out the phase shift and know what it is. The next pair after 0, 0 is 1, 0. Now 1, 0 translates to 270 degrees. So 270 degrees, we kind of start at 0 and then we go downwards. So you see that kind of thing here, and then we've got all our other discontinuities. In case we just repeat a pair, so 1, 0 and another 1, 0, so that means there is no discontinuity, because we kind of arrived where we have, and then we start from the same place. So this is an example. Again, you don't have to understand every single detail of it or remember exactly what these phase shifts are, but I just wanted to convey to you the technique that we use when we do BPSK or QPSK. So now when you hear that word BPSK or QPSK, you'll understand exactly what we do. In QPSK, we take the bit stream, we divide it into pairs, we encode each pair into a phase shift, and then we impose that phase shift onto our oscillating carrier wave. Perfect. And so now I want to talk about the most important modulation scheme, which is called QAM or QAM, and that stands for quadrature amplitude modulation, as I may have said before. No, I didn't. So QAM is quadrature amplitude modulation, and that helps us to make larger groups of bits. So if we were to just continue doing what we did before, right? So before, what we did is we just kept using different phase shifts. If we were to do this here, it would become impractical. Why? So let's just suppose that we wanted to do 1 of 16 phase shifts, because we wanted to group together 4 bits. So when you group together 4 bits, because we want to transmit at a higher air capacity. So when you group, when your groups are larger, when you've got 4 bits in a group, that means you've got 16 different combinations. So here I've drawn what a phase shift modulation would look like if we had 16 phases. And you see that these green dots come progressively closer together. So, the distance between the dots, between this dot, which codes 0, 0, 0, 0, to this phase, which codes 0, 0, 0, 1, is quite small. And we don't like to have small distances between these phase shifts, because that makes it all the harder for the receiver to make out what we're transmitting. We're not going to be talking about receiver today very much, just a little bit, but you understand that if at the receiver there's a little bit of noise, the receiver may then see, oh, well, we transmitted a 0 degree phase shift, but the receiver might mistakenly make that out to be however many degrees we have here. So that kind of becomes untenable at some point. And so what we like to do is play not only with the phases, but also with the amplitude. And that is QAM or quadrature amplitude modulation. And I would say most, if not all, modern communication systems use quadrature amplitude modulation. So we vary or we manipulate not only the phase, but also the amplitude. And this is what it would look like on our little diagram. So here's a little diagram, remember, where we've got, that is our 0 phase, this is our 90-degree phase, this is our 180-degree phase, and so on. And if I look at this green dot here, it's got some phase, something close to 0, not 0, maybe around 20 degrees. Okay, so that would be, that green dot here would correspond to a phase shift of 20 degrees. And it's also got an amplitude. So an amplitude is how far is it from our origin, right? So obviously this dot here has a higher amplitude than this dot here, because this dot here is just closer. So the distance between the origin of the graph and the dot, that tells us the relative amplitude of this particular group or symbol. So we would consult this table to see what the amplitude is, and we would also consult this diagram to see what the phase was. So, and then we go about assigning different bits to these different dots. So for example, I might assign the combination 0, 0, 0, 0 to this dot here. So that would have quite a large amplitude, right? To go from the origin all the way here, that's a large amplitude. And as I've drawn it here, it would have a phase of -45 degrees. So I would kind of like, instead of going from here 45 degrees, I would go all the way around to reach here. That would be 225 degrees, right? So that is kind of that dot. And then another dot, which with another combination of phase and amplitude, would correspond to another quartet of bits. And so on, all these 16 dots correspond to the phase and amplitude of all the possible combinations of 4 bits. So we don't necessarily have to just group 4 bits together, which would make 16 QAM. Why 16? Because 4 bits give us 16 different combinations of quartets of bits. But we could group more. So we could, for example, group 8 bits together. And when we group 8 bits together, that will give us 256 different combinations of 8 bits. Okay, if you think of 8 bits as a byte, you probably know that bytes range from 0 to 255. So there are 256 different combinations of 8 bits. So if we were to do this, if we were to take our stream of bits and group it into groups of 8, we would call that 256 QAM, okay? And this is what a QAM actually looks like. So as you can see here, we have our phase shifts, which I explained before, you know, in circle here, but notice that we also vary the amplitude. So we've got a low amplitude and we've got a high amplitude, right? Depending on the distance between each of these dots here that represent a combination of bits, the distance of that dot from the origin. So that is what a QAM signal looks like, right? So if you were to look at it, and it is possible to actually look at it, this is what you would see with special instrumentation. Of course, this is what you would see. Okay, so just to summarize, because we're coming to the end of section 2, so modulation is a way of modifying a carrier wave to carry information. And in modern digital systems, we use QAM, where QAM means we vary both the amplitude and the phase. And if we use higher order QAM, we get a higher data rate because we're grouping more bits into each one of our symbols or into each of our instances of our transmission. But notice, and this is really maybe perhaps unintuitive if you're just looking at this first, is that as we grow our QAM, our advantage or our benefit diminishes. So for example, if we go from 128 QAM to 256 QAM, all we've done is 128 means we've grouped 7 bits together, and 256 means we've grouped 8 bits together. So the improvement in our speed, in our transmission speed, is only 8 by 7. It's only about 14%. So we went from 128 QAM to 256 QAM, and our air capacity only increased by 14%. So this is just a guideline. It's not exactly, but it is around that number. So, you know, we do get more. We are able to transmit more across the link. But like I mentioned before, there is a penalty. And the penalty is that the higher, the more different combinations of phase shifts and amplitudes that we use, then the more prone we are to errors at the receiver. And I'm not going to talk about the receiver today, but just to give you an idea, because I think it's important, these diagrams here show different modulation schemes. So if we start with the one on the left, this is BPSK. And as you remember, BPSK means one of two phases. So here they've mapped bit number 0 into 180-degree shift and bit number 1 into a 0-degree shift. It's fine. You can do it whichever way you like. But basically, we've got two possible phases. But at the receiver, due to noise, when the receiver tries to work out what phase was transmitted, it would actually work out these blue dots. So we might have transmitted a 0 phase shift, but it might have been received as a different phase, right? This has got a different phase you can see here. So all these different points correspond to different phases and different amplitudes. And it's not because we transmitted those combinations. We only transmitted one of two combinations, but the receiver, due to noise, received all these blue little dots. Now here, because the distance between 1 and 0 is quite large, right? There is, you can see here the distance is large. It means the receiver can tolerate quite a lot of noise before it starts making errors. You know, that is quite immune to noise. But if we go to higher QAM, like you see here in this diagram, so here we would have 64 different combinations of phases and amplitudes. And so the difference, the distance or the separation in phase and amplitude is quite small between each of these, say, adjacent combinations of amplitude and phase. And so in 64 QAM, we can't really tolerate as much noise as we could tolerate here. Because if we had the same amount of noise, you see where the dots, the kind of radius where the blue dots fall here, we would just make tons of errors because the receiver would just map them into completely different combinations of phases and amplitude. So that is why when we go into higher QAMs, we pay, right? We pay with sensitivity. It means the receiver can't tolerate as much noise as a low order QAM system could. Okay, so hopefully you know all about QAM now, and I want to talk about what we do to prevent these kind of errors. So just to say, for example, if we go back to BPSK, because that's simple, if we were to transmit 1, but the noise would take that all the way across to here, the receiver would say, aha, that must be a 0. And the receiver would say a 0 was transmitted, where in fact a 1 was transmitted, and that is an error. So we have techniques of fighting, of combating, of mitigating these errors. And I'm going to talk about that now. I'm just conscious of the fact that it is 12 o'clock. So those of you who originally allocated an hour have to go. Thank you very much for joining me. And if you're interested in hearing the rest, just, you know, tune into the recording. And those of you who are able to stay with me a little bit longer, then please do. So the way we fight these errors, the way we mitigate these errors is called channel coding. Okay, and there are various different ways, techniques to do channel coding. I'm going to talk about forward error correcting codes. That's sometimes abbreviated to FEC, okay, forward error correcting codes. And what we do here is we take our information bits, you know, our stream of information bits, and we add more bits to them. These bits that we add are not information bits. They are extra bits, and they're cleverly chosen to create a correlation between the bits that are being transmitted. So it sounds like a mouthful, I know, but I'm going to show you an example and you will understand in no time. So what do we do? Let's just suppose that we're doing something like, you know, we're looking at the bits and we're dividing them, the information bits, and we're dividing them into pairs. So say we have a pair of 0, 0, which is something we looked at before. Now, instead of just using QPSK to map the 0, 0 into one of 4 possible combinations of phase, we add more bits to the 0, 0. So here in orange is our original 0, 0, but you see I've added something on the left and I've added something on the right. So I've transformed the 0, 0 into 5 zeros. And if I had a bit stream of 1, 1, I would retain that, but I would transform that into a quintet by adding 1 in front and 2 behind, 2 trailing zeros. So you see how our pairs of bits transform into quintets of bits, right? And that means that instead of just having 4 possible combinations, because when you're looking at pairs, you have 4 possible combination of pairs, which are, of course, 0, 0, 1, 1, 0, 1, and 1, 0. So instead of just having 4, which means we would be able to use QPSK, now we have 5 different bits. That gives us 32 different combinations, because 2 to the power of 5 is 32. So we've got 32 different code words. Not really, you know, we would only be using 4 different code words because we only have 4 types of pairs. So let's see how that works. So I am transforming 0, 0 into this code word, which is just 5 zeros. I'm transforming 1, 1 into 1, 1, 1, 0, 0, and I'm transforming 0, 1 into whatever it says here, and 1, 0 into whatever it says here. So even though there are 32 different combinations of 5 bits, only 4 of them are legal, okay? Only 4 of them are really possible, because I only have 4 possibilities of information bits, because I'm only looking at pairs of information bits. So these bits that I've drawn here in orange, they're the actual information bits. So they relay the email, the web browsing, the voice over IP, whatever it might be. The black bits are extra bits. They're like stuffing bits, right? I've just added them in a clever way and really inflated my the information I have to, or the bit stream that I have to transmit. Now, why do I do this? The fact that only 4 combinations of 32 are legal means that the receiver is now able to both detect errors and correct errors. And I'll show you how that works, right? So let's just suppose that we have the, the arrangement I've described so far. And let's just say that because of noise, the receiver sees 1, 1, 0, 0, 0. Now, 1, 1, 0, 0, 0 is none of the possible permitted and legal code words which we had here. So the receiver looks at this and says, aha, something's gone wrong, because 11000 is not a legal or permitted code word. So what the receiver will do now is it will try to guess which of the 4 original code words that are possible or permitted or legal was really transmitted. And in order to do this, it compares them. It compares the received word to the 4 legal permitted code words. And the way it's compared is by looking at something called Hamming distance. Now, Hamming distance, that's quite technical, but it's really easy to understand. It just counts the number of places where the bits are different. So, for example, if I compare the received word, which is 1100, to a permitted code word, which is all zeros, then there are differences in the first position, because instead of 0, I received 1. And there's also a difference in the second position, because instead of 0, I received 1. But the other 3 positions are the same. So because I had a change in 2 positions, we call that Hamming distance of 2. Okay, and then we also then compute the same distance to the second code word, which is 11100. And then we compare that to that, and we see that there's only 1 bit different, right? So that means there's the Hamming distance of 1. If we compare it to the third code word, which is 00111, we see that all bits are different, right? So all 5 bits. Hence, the Hamming distance is 5. And then we do the last code word as well, and we see 2. Now, we say, okay, well, what's more likely? Is it more likely that this word was transmitted and 5 bits got wrong? Or is it more likely that this code word was transmitted and 2 bits got wrong? Or is it more likely that this code word was transmitted and only 1 bit arrived wrong? And so looking at the odds, we say, okay, it's a lot more likely that this code was transmitted, right? That's the one corresponding to 11, that was transmitted. And so we guess that the information bits were 11, okay? So here I showed you an example of how we actually corrected an error, Okay, there was an error and we corrected it, right? And we guessed correctly the information bits that were transmitted. Now we had a penalty to pay because obviously instead of transmitting 2 bits in QPSK, we're now transmitting 5 bits, which is 32 QAM. Okay, and 32 QAM we talked about before, that's a lot more prone to errors. So this, of course, is an exaggerated example. We would never add 3 coding bits to 2 information bits. We would add a lot less. We would add a fraction. We would maybe add, for example, 5 bits to 200 bits of information, right? We would take 200 information bits and we might just add 5 extra bits, right? So the overhead is a lot less, but this was just an example to explain to you what forward error correcting codes is. So hopefully you understand that. And again, that's something that implemented today in almost all modern communication systems. Okay, so just to complete this, I put here in this table, just if any of you wanted to follow, all the possible 32 combinations. So if you count all these quintets here, right, here, 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 and there, you would see that there's a total of 32. So these are all the possible combinations, and the ones here, they're all correctable. Why are they correctable? Because there was only a single error, a single bit was inverted. We also have a case where some cases where 2 bits are inverted. For example, we started with all zeros, but we got 1 at the beginning and 1 at the end. So that means 2 bits were inverted. So in this case, we're able to say there was an error, but we're not able to correct the error. Okay, this is called error detection. And error detection is also important because we can push that up to a higher layer. For example, we can push that to the MAC layer or to the TCP layer, whatever higher layer we have, and just tell them, look, we know there's an error. We're not able to correct it, but there is an error, and then the higher layer can often do something with that information. Okay, guys, that completes our second topic, which is modulation, and I'm about to go to wireless propagation. Now, you're all very, very silent. I've got no questions, so either I'm exceptionally clear, in which case, thank you very much, or you've all fallen asleep. I do hope it's the former. So I'm moving on to the third topic on here, which is a completely new topic, and that is wireless propagation. Okay, so wireless propagation basically is how we get the signal to move across from the transmitter to the receiver. I was going to say to move across over the air, but as we all know, we don't actually need air for that to happen. You know, we have wireless communication in space where there's vacuum, there is no air. So air is not necessary. It's just how we get those carrier waves, those modulated waves, to move from one point in space to another point in space. So here are the general principles, right? So as a transmitter, you already know. So we take our information bits and we encode them using something like the forward error correcting code that I just discussed. Then we use this code words to modulate a carrier wave, right? So we change our perfectly oscillating carrier wave by slightly modifying the amplitude and the phase. Then we have a power amplifier, which takes that modulated wave and amplifies this. And I call PTX, I use that to designate the power at the transmitter. And that goes onto an antenna. Now, the antenna, as we learned before, focuses this energy in some direction. And the gain of this antenna is how much it focuses that energy compared to an isotropic antenna. And I denote this as G gain TX because we're talking about the transmitter. So here's what it looks like, right? We've got a radio with an output power of PTX, and that goes to an antenna that focuses that in a particular direction, antenna gain GTX. Now, on the way, and this is really the interesting part, on the way, 2 things happen. We've got losses and we've got distortions, right? So the signal, as it propagates, it gets, it loses its energy, so it becomes weaker and weaker, and it also gets distorted occasionally. And then when we look at the receiver we have the receive antenna. So the receive antenna helps us capture more of that transmitted wave. So the more it captures, compared to an isotropic antenna, we call that the gain. So GRX, the gain at the receiver. And then at the output of this antenna, we've got some power level, and I call that PRX. So that is the power at the receiver. And then, of course, the demodulator, the receiver, demodulates this to discover all the different phases and amplitudes and the triplets or quartets or quintets or however many bits that corresponds to, and that gets decoded like we talked about before to reveal the information bits. So what I want to talk about now is just give you an idea of these losses and the distortions. And you know, if you guys work with wireless communication, it's important that you know that. So the first loss I want to talk about is sort of, I call it the built-in loss, okay? Or the mandatory loss, right? This always happens. And so we call this free space loss. And what is this free space loss? So basically, as the transmitter sends away those carrier waves or modulated carrier waves, they propagate a little bit like a ripple in a pond. Now, it's true that we're using an antenna to focus them more in a direction of interest, right? But even though most of the energy will then go in the direction of interest, still some energy goes all around like a ripple in a pond. And obviously, the further away we get from that transmitter, the ripple has expanded more and more and more, right? The radius of these circles becomes larger and larger. And by the time we get to our receiver, the receiver is only able to capture a part of that huge ripple, right? And that part corresponds to the size of the antenna. So obviously, if we had a huge antenna, we might be able to capture more. But we have a finite size, so we're only able to capture some of that propagating wave. And because we're only capturing this part, which I've drawn here in purple, just this purple part, as opposed to the whole circle all around, or the whole ring all around, that is a loss. Okay, we've lost most of the signal, really. You know, we're only capturing a bit of it. This loss is called free space loss, right? It's always there, right? Can't get away from that. And there's a simple formula to calculate what the free space loss is. So you take the frequency in gigahertz, and you take the logarithm of that, base 10 logarithm, you multiply that by 20. Then you take the distance in kilometers, again, you do the logarithm of that and multiply by 20. Then you add these numbers and add 92.4, and whatever you get, that is the loss in dB, or free space loss in dB. Now, the 20 log might look familiar to you, okay? It looks a little bit like decibels, remember, because decibels were 10 log. Here we're doing 20 log for some technical reasons I won't go into, but essentially this formula is in decibels. So here's an example. Say we've got a Siklu link operating at 75 gigahertz, propagating over 1 kilometer. So I would do 92.4 plus 20 log 75, that's the 75 gigahertz, plus 20 log 1, that's the 1 kilometer. And you would use your calculator to compute that, and you would get 130 dB. So that is the loss, 130 dB, right? So we've lost, going from the transmitter to the receiver, 130 dB. Now, 130 dB, you now know, is 1 divided by a really large number, basically 1 and 13 zeros. Okay, not sure what that is. I think it's 10 trillion. Okay, so we've lost all but one part in 10 trillion by the time we reach the receiver. Okay, it's really a staggering number. Okay, now as a rule of thumb, you might want to know that every time you double the distance, and you can see that it's because of the 20 log, you would have to add 6 dB to the loss. Not 3 dB as we said before, but 6 dB. This is on account of the 20 log. And then every time you double the frequency, you add 6 dB in free space loss, which I designate LFS, loss free space. So when we go high up in frequency, we lose 6 dB more. And you know, here in Siklu, we work in really high frequencies. That's not very nice to lose that. But actually, we gain because, and this is something I've not covered today, but every time you double the frequency, you gain 6 dB in antenna gain for the same size antenna. So say I'm looking at a 1 foot antenna and I compare this antenna operating at 30 gigahertz as opposed to 60 gigahertz, for example, we gain 6 dB. And because we gain 6 dB at each antenna, one gain cancels out by the additional loss in free space, but we actually end up with a net gain of 6 dB. So it's great to use high frequencies. Okay, so that is free space loss. That is inherent. That is always there. That is physics. That's nothing we can do. This is because of these waves rippling in a pond and our ability to capture only just a small part of it. Other losses that we have en route is due to atmospheric gases. That obviously only applies to terrestrial transmission, not to space transmission. But we do have to take that into account. So we've got two types of gases that really count in the atmosphere. There are others, of course, but they don't really count. So the one is the water vapor, which we have in the atmosphere, and the other is the oxygen. So with water vapor, that is approximately, at least when we're talking about wireless communication, that's pretty much constant. I would say around 0.5 dB per kilometer or less, so it's not very much. So that's what the vapor does. But when we go to higher altitude, like to mountain tops, then the density, obviously, of the water vapor diminishes, and then it would be a lot less than that. But it's not very much, 0.5 dB per kilometer. Oxygen is interesting in the frequencies that Siklu operates in because we have very high oxygen absorption around 60 gigahertz. So up to 15 dB. Okay, so 15 dB, now we know what that means. 15 is 10 plus 5. So 5 dB corresponds to 3. So that 15 dB is 30. So basically, after the signal at 60 gigahertz propagates 1 kilometer, only one part in 30 remains. And when it propagates another kilometer, then one part of 30 in that. So basically, we ended up in one part in 900 that survived 2 kilometers. So that is definitely something we need to take into account when we talk about losses due to oxygen. And then another very important loss is loss due to precipitation. And this is really the big killer in high frequencies, right? So it's very significant above 18 gigahertz. If you're kind of working at frequencies below that, don't worry about rain. But if you are working at 18 gigahertz or more, yes, you have to pay attention to rain. Now, the loss due to rain is proportional to frequency. So the higher the frequency, the higher the loss, and also to rain intensity. The more intense the rain is, the more you lose. And here's an example that's relevant to Siklu. So if you operate at E-band, the attenuation due to rain can be as high as 20 dB per kilometer, right? 20 dB is 1 part in 100. So we lose 1 part in 100 every kilometer. Okay, so that is very, very significant. After 2 kilometers, that is 1 part in 10,000. And after 3 kilometers, that's 1 part in 1,000,000 that survives the rain. So very, very significant. Okay, so these were the losses. And now I've got about 5 minutes to go, and I want to talk about distortions. So the most important and the most significant distortion is something called multipath. Multipath is really an echo. So remember we talked about a simple schematic where we've got a beam going from the transmitter to the receiver, drawn here in yellow. But if the transmission beam is quite wide, that beam can also reflect off a surface, say the ground or the roof of a building, or if it's a body of water, off the water, right? And it can reflect. And then the receiver will then receive two beams, the direct beam, the yellow beam, but also this reflected beam, which is this purple beam. Now, the problem with this reflected beam, the purple beam, I mean, there's nothing wrong with it. The problem with it is that because it took a longer route, right, you see the distance it had to travel is a lot longer than the direct beam. Because it took a longer route, it means that it's delayed compared to the direct beam. And this delay causes really a big problem for the receiver. And we call this, basically messes it up. And we call this selective fading. And I wanted to show you an example of this in a minute, but just to say that this kind of multipath, this is quite important, prevalent, and also significant in low frequencies, because in low frequencies, the transmission beams are wide. So there's, they will and they do reflect off surfaces. So multipath can be really, really bad. And it's very hard to predict it as well. It's very hard to say, well, how often is it going to happen and how often is it going to mess up my transmission? And at high frequencies, so again, we've got a typo here, so apologies for that. This should be high. So at high frequencies, the transmission beam is very, very narrow. And so this problem never occurs. So for example, here with our 1-foot antenna, we've got a 1 degree beam width. So there is never any reflection, or if there is a reflection, it's way off the mark. It's never received by the received antenna, right? So if you are doing Siklu, that's great. No need to worry about multipath. If you're doing something else, you do need to worry about this. And I just gave you an example here of what happens. So we start, this is an example of BPSK, right? So now we know what BPSK is. So we start with BPSK here, and remember with BPSK, we're just using 2 phases. And so the amplitude of the signal, this green modulated signal, is constant. And all we have are these phase shifts that we talked about before. Now, the reflected beam is going to be delayed. So you see here, I've delayed it compared to the direct beam. But also it's slightly attenuated because the reflection causes an attenuation. So that is a direct beam, and this is the reflected beam. And when you add these two together, just mathematically add them together, you end up with this yellow signal here. And this yellow signal, when you look at it, it looks nothing like BPSK, right? BPSK is supposed to look like the green signal. What we get is the yellow signal. And this is really how the multipath of the reflected beams mess up the signal. So hopefully, it's a lot more complicated than this actually, but hopefully you can appreciate what multipath does. Right, I'm running out of time here. So just to say that, all of you, I guess, are familiar with Wi-Fi routers, and you know that Wi-Fi routers are the good ones, have multiple antennas. And why is that? Is because when we have these this multipath, sometimes you can get better multipath, less severe at one antenna as opposed to another antenna. And there's also the ability to add the signal of these 3 antennas together to mitigate this multipath. So, there are ways to fight this, but it is quite nasty. Right, very quickly, another thing that can happen is something called beam spreading. So beam spreading happens when you've got different layers of or layers in the atmosphere of different temperature, and the refractive index of air at different temperature varies, and that causes the beam to bend away. So that might cause the beam to bend, and so instead of now the beam being focused at the receiver, it's now focused in another direction. Okay, it's basically like deflecting the antenna. So instead of perfectly aligning the antenna, deflecting it, right? And this is only significant in really long links. So fortunately for us at Siklu, we don't have to really worry about this because our links are relatively short. Another thing to talk about when it comes to distortion and losses is something called diffraction. Diffraction happens when an electromagnetic wave or a beam just grazes an object. So here you see our beam just grazes the top of the building, and that causes, again, the beams to kind of diffract or spread in different direction. So not all the energy that was transmitted reaches the receiver, you see, because some of it gets deflected and that doesn't arrive at the receiver, so that is a loss. Okay, and again, in Siklu, we don't have to worry about diffraction because we require a clear line of sight, so there's never any, we never have to contend with this kind of thing, whereas in lower frequencies, you do. So hopefully I've given you a good general understanding of how waves propagate and what are the losses that we have to look into and what are the different types of distortions that we have to look into. Those of you who will join me next time, we will look at this in more detail as it relates to Siklu. Not next time, sorry. So number 3, lecture number 3, which is in 2 weeks' time. That's it for me. So for those of you who persisted with me, thank you very much. I don't know if there are any questions. I can't see any.
I can't see any. No, just Lucian saying thank you very much.
Excellent, Carla. I'm glad to hear you. So at least I know there's one person hearing me.
I'm here, yes.
You are here.
I was just going to say, well done for wrapping up at pretty much 12:28. So it was fantastic, good timing, and really well delivered. So yeah, thank you again, Daniel, for delivering that content today. It's been really, really good.
Yeah, you're very welcome, and please send any feedback to me at this address, daniel.e@siklu.com. And thank you very much, everyone, and thank you, Purdicom, for hosting this event.
Yes, thank you. And just to reiterate to everybody who's still here, we have recorded the session, so I will send out the recording, and yeah, you'll be able to provide us with feedback on this session off the back of that email as well. And I'll also send a link to the other 2 sessions as well, because we've got another one next week and the week after. So if you haven't signed up to those already, do take a look. It'd be great to see you on those ones as well. So yeah, thank you very much. Thanks to everyone who attended. And thanks again, Daniel.
Pleasure, anytime. Have a good day, everyone.
Thank you. You too.